So good morning, everybody. Thank you for joining us this morning. My name is Cesar Saavedra, and I'm a product marketing manager at Red Hat. And with me today is Thomas Qvarnström, and he's a technical marketing manager with Red Hat. And today we're going to be talking about cloud native application development, the path to it, and we're going to give you 8 steps or 8 recommendations for you to take away in your journey to cloud native app dev. So first of all, I'd like to go over the evolution of cloud frameworks, applications, and services. The concept of running your workloads off-premise is nothing new. It's been around since the 70s. Back then, there used to be these networks called VANs, value-added networks, and they were specialized on running EDI workloads. So organizations would hire, basically run workloads on those VANs with dedicated connections to them. So in the 80s and 90s, the internet became popular, and then I don't know if you remember, some of you remember the concept of co-location, right? So organizations sometimes they would, instead of running their own data center, they would run their servers off-premise. As the internet became more reliable, Amazon appeared in the market in 1994. And then also Compaq coined the term cloud computing in 1996. And when people started getting comfortable with using the internet, VANs kind of became the old thing, and people started moving to the internet as a means of communication. And RosettaNet, protocols like RosettaNet became popular. You can, for example, run EDI messages over RosettaNet over the regular internet. That was in 1998. Salesforce, the largest SaaS provider in the world, launched in 1999. Then in 2001, the Manifesto for Agile Software Development came about. EC2, the largest compute as a service provider, came into the market in 2006. Netflix streaming appeared in 2007, together with the iPhone, that really exploded the presence of the digital presence of everyone. And using your phone became a new channel for businesses to communicate and sell through consumers. In 2009, Java EE introduced CDI and the concept of profiles. Uber also was founded in 2009, which also is, a born in the cloud company. Netflix coined the term cloud native in 2010. Dropwizard, if you heard of the concept of fat jars, Dropwizard is the company that made those popular in 2000, and they came into the picture in 2011. Heroku, if you've heard of 12-factor app manifesto, Heroku, they came up with that in 2011. The first microservices assess came out in 2012 by ThoughtWorks. Docker came into the picture in 2013, followed in 2014 by the microservices definition by ThoughtWorks, Mr. Fowler. And Spring Boot also, version 1 was GA'd in 2014, together with Kubernetes. And nowadays we live in a world where containers, microservice, the cloud, open source are all a common thing and accepted in production, to run workloads in production. I'm gonna do this. So nowadays organizations, they see themselves with existing workloads. They've been running their businesses with systems that have been running for years. And now they have to adapt to applications that have to run on the cloud and have to be agile. So they have to support DEVOPS types processes, as well as old style waterfall development processes. So IT needs to adapt, and people talk about digital economy, and this is the reason that businesses have to change basically. And not just because of the market needs, but also because being digital pays off. So there was a study by Capgemini and the MIT Center Research where they analyzed many organizations, and they identified that digital leadership, or companies that have gone digital, were 26% more profitable. They were 12%. They had 12% higher market evaluation, and they had 9% more revenue than non-digital equivalents. So it does matter to adopt these new techniques for agility. Now, to speed up the development and delivery of applications, we think of this yin and yang relationship between what we call application services, which speed up the actual development of your business application, and the infrastructure services, which speed up the delivery or deployment of your application. And they both go hand in hand. Sorry, did I miss something?
Yeah, this is switching.
Okay, is that right?
Oh, sorry.
Sorry. Oh yeah, I didn't switch. Okay, sorry. Thank you. So, so what is cloud native app development? So, when we talk about cloud native app development, we think about these 4 quadrants. Okay, we think about an approach for building and running applications that takes full advantage of the cloud computing model based upon these 4 key tenets. And the key tenets are service-based architectures, whether it's data services, integration services, microservices, mini services, data services. I think I mentioned that. But it's based on services. The communication is based on APIs. Okay, this is inter-service communication, and the infrastructure is based on containers, and the processes are based on DEVOPS. Now, if you look at the quadrants on your left, the service-based and API-driven, they have to do. Remember, I talk about the yin-yang. The development concerns are the service-based and API-driven. So those help you with the actual development of the business application. And the containers and DevOps, they help you with the deployment and the delivery concerns of cloud-native application development. Thank you. So when we compare traditional and cloud-native app dev, these are the differences. When it comes to focus, traditional focus is longevity and stability, whereas with cloud-native, it's speed to market. The development methodology is waterfall and semi-agile for traditional, whereas with cloud-native is agile development and DevOps. Teams in traditional app dev are usually siloed, so you have your development team separated from your ops team, separated from QA and security. In cloud-native is a collaborative effort within DevOps teams. The delivery cycle, within traditional is usually long. With cloud-native is short and continuous. Application architecture is tightly coupled and monolithic for traditional, and cloud-native is loosely coupled, service-based and API-based communication. And when it comes to infrastructure, traditional is usually server-centric. It's designed for on-premise. It depends on the infrastructure, scales vertically, and you have to pre-provision for peak capacity. And when it comes to cloud-native, it's usually container-centric. It's designed for on-premise and cloud. It's portable across infrastructures, whether it's on-premise or cloud. Scales horizontally, and it's it responds well to on-demand capacity. So now let's move in to the actual 8 steps. So we're going to give you 8 steps. You don't have to do all of them at the same time. You can pick whatever steps make the most sense for your organization and start with those. And you can start in phases, and at every pass you can implement a little bit more of that step, whatever steps you decide to start with. So the first one is evolve a DevOps culture and practices. As I mentioned before, there are many new technologies, faster approaches, as well as in cloud-native application development, you have tighter collaboration across different teams. So organizations realize that evolving a DevOps culture is important. In fact, an IDC past view for the developer survey done at the end of last year revealed that 51% of large organizations had already adopted DevOps processes. And within those, 20% were using DevOps for only 10 to 40% of the application. So there's still room to grow in that case. But doing DevOps brings many benefits. So for example, there is integrated and collaborative approach across teams. It encourages experimentation. Fast failure is the normal operating procedure. There's transparent decision making. It boosts trust and cooperation. It catalyzes innovation. Teams rapidly build prototypes, and organizations adopt the agile workflows when they adopt DevOps culture. And now I'm going to pass it on to Thomas to continue.
Thank you, Cesar. So, but how about existing applications? When we're talking about cloud native applications, we sometimes use the unicorns to bring up, which has the luxury of start from a clean sheet. They just develop new applications, they can adopt new features, new processes. But most organizations actually have existing applications, existing processes, etc. So we need to modernize those applications as well. We need to speed up the delivery and get the benefit of using cloud native applications for those as well. So one of the things to consider, one is to actually take your applications and lift and shift it over to a new platform that supports being more agile for us, that can support quicker deployment, quicker releases, quicker support, etc. So for many organizations, that is a container-based platform, like a Kubernetes-based platform, or like OpenShift from Red Hat. But that typically also requires actually that you look at the runtime you're using. So luckily, there are often very similar runtimes that are adapted for cloud native applications. So for example, JBoss EEP is one of our Java EE fully certified application servers that can run perfectly nice in a container-based platform. It's nimble and nice and agile, etc. So the first step in speeding up the application would be to move that platform into a container-based platform. While we've done that, we can then start and work and experiment on that monolithic application and start actually breaking that monolith application apart. We call that pattern strangulation. And that would mean that we actually start to modularize our application, our monolithic application, into different modules, exposing APIs for those modules, and then break out particular services into their own containers and their own runtimes instead. So this will enable us to move faster and deploy faster over time. One thing that we need here is and what's part of Kubernetes platform actually is an intelligent routing type of where we can route traffic to the correct type of service. If we want to do even more advanced routing, we can use products like an API manager like Freescale or Istio, which is coming into Kubernetes now as well. So we're going to see that in a demo later on that we're going to run. And we need to speed up, and eventually when we broke down the applications, we can actually break it down into mini or microservices. And the main reason we want to do that is to be able to deploy faster and deploy new functionality, deploy quicker into production. However, we also have to consider there are other services around here, and we should try to use the existing application services we have. So one pattern we have to stay away from is building our own on everything again. So meaning with that is that we need to use existing services that can exist for example, caching, to get performance out of that. So there's in-memory data grids, there are messaging, there are rule management systems, integration connector, and things like servers, etc. Applications, and to speed up the development, we should actually try to reuse those services that exist in these platforms today as well. The fourth thing is to choose the right tool for the right task. So as a developer, you have tremendous power nowadays. And as a developer, you have the power to choose which development framework you want to use. But we have to realize that most applications designed in the cloud native fashion will use different languages, multiple languages today. So most organizations will not standardize anymore on one single platform or one single technology, one single runtime. Actually, the surveys shows that that most developers employ multiple languages, and 87% of the respondents are considering multiple technologies for microservices, for example. So these are just a few of the examples that could be there. And actually, we're going to look at a demo why that is important as well and how that looks like. So I'm going to switch mode a bit into a demo, and this demo is built on an application that we call COOLSTORE. It's basically a store where you can go in and buy cool stuff that are red at, logoed, etc. So this COOLSTORE has an architecture where we simply have a product catalog, and that's a list of different products that's being displayed. But it also has, for example, inventory data here. And how that looks like in an architecture for microservices is like this. So in the bottom, we have the catalog service, which only contains data around products. It doesn't contain the inventory status, it doesn't contain prices, for example, or things like that. We also have a service called inventory service, which contains the inventory data for each product. So to do that correctly and nicely, we also use a pattern in microservices called a gateway. A microservices gateway that would actually, the first thing that would happen is we'll ask the catalog for all the products and get the product list back. And in this case, it's 8 products it gets back. And then it queries the inventory for the inventory data of all those. So that obviously will create 8 requests down to the inventory. And this is one of the patterns you'll see in microservices happening a lot. For a simple example like this, we could replace it with something else. But in fact, that's how a microservices architecture looks like. It's distributed. We have a lot of service-to-service calls going on. So this is a good example. So I'm going to show you a demo where we implemented this gateway using 2 different runtimes. One is the more traditional runtime, which is based on the synchronous type of applications that we've been using for many years in Java EE and in Spring, etc. And the other one is using a reactive framework, in this case Eclipse Vertex. So I'm going to switch mode over to that. And I actually realized when you were talking, I realized I didn't do my cleanup enough. So I'm going to have to do one more thing. And I'm going to do, so you can ignore this. Sorry. Delay. Oh, sorry. So now we should be ready to go to the presentation here. So this is the application, and if I reload this page, it responds quickly. And this is now using the traditional one. So this is based on Spring in this case. It could be a Java EE or anything that's based on a synchronous type of application that we're writing. And it looks to be responding nicely and everything. And what I've done is I've used what's called a distributed tracing here called Jaeger. So we have Jaeger here, and Jaeger can do distributed tracing of all the hops doing in between the different services. So this one should, let's reload that one, and now we can see some data, and we have a gateway here, and the operation is called gateway route Spring. So if I look at this and I find traces here, there's no traces, that's typical. Let's reload this a couple of more times. Oh, do you know why? I have a minimum here of 1 second, and it's responding faster. So here we go. So here we have our traces, and if I click on one of the traces here, we can see what's going on. So we can see, actually, our service, let's first see this. In duration of this call is 40 milliseconds, which is quite good. We don't have to worry about that. And this is what happens when the developer develops. He shows and looks 40 milliseconds, that's acceptable, it's within our limits, let's go live with this. But actually, when you start tracing and see what's going on behind the scenes, you can see here that actually we're doing a lot of calls to the inventory service. So here, first thing we do, we did a call to the catalog service. It responds quickly and nicely, and therefore we do calls to inventory service. and these are made in sequence after each other because we're doing synchronous programming in here. And that will, of course, what happens if we were to introduce and put this in production, and actually our inventory service isn't this fast as we say. Here the inventory service responds in like 1 millisecond. But what happens if that will be 200 milliseconds? So one thing we can do, which is nice in a container-based platform, in this case I'm using Istio for that, is we can actually introduce faults. So I'm going to introduce a delay in here. So if I do inventory, if I learn to spell, well, so I'm going to do there, I'm going to introduce a delay route, and I'm actually going to go and edit that for you as well. This is a bit technical. And you can see that this is a delay rule that for the destination inventory, it has a fixed delay of 200 milliseconds. I'm actually going to replace 50 here and say it's going to be for 100% of the calls. So let's do that and save that. And as soon as I've saved that, I now introduce the delay. So I can test how is this going to produce in production. So let's go back to our application here. And now let's go back here and let's reload the application. We'll see that it's much slower. Still responding, but much slower. So let's see what that looks like in the tracing as well. So I'm going to go to the tracing tab, and I'm going to go back here, and this time I'm going to do the same thing, but I'm going to say mean duration 1 second here. And we can see we have 3 traces here showing 1.6 seconds in response. So if I go into one of them, you can very, very clearly say, you know, what's happening when we have a delay in one of the background services. So that's, of course, will cause issues for us. And it's actually worse than that. What happens is that we're tying up a lot of resources in the original gateway here. We're tying up resources that's going to affect the other threads that are being tied up in requests. So actually, let's put this under a bit of load as well. And I'm running out of time here as well. So I'm gonna put some load, and I'm gonna put 10 concurrent user doing 10 requests for this, and it will probably go fine with 10 requests. And we can see that, yeah, it's responding. Well, actually, we had one issue at least, but we had one issue there. You saw red. And if I let's break out of this, and if I do, and I add just a bit more here, let's do 12 users, 12 concurrent users. I'm just gonna wait a little time to make sure that it's recovered from the original. Oh, that was a lot of issues. And so what we're seeing here is actually that the application server is running out of threads. And when it's running out of threads, it responds quickly with, I'm busy, I can't treat you anymore. So obviously that's not good in a microservices environment where we want to have distributed, we want to high performance. So I'm going to switch now, and we're going to change the routing rules. So I'm going to we have a routing rule in here. Let's do clear so you can see here. Also get route rule. So I'm going to delete the spring route rule. This one. And I'm gonna create a vertex one instead. And the vertex one, so now when we go to the vertex one, we still have that delay, by the way. But if we go here, it should now show up here in the corner, it should show that we are using a reactive framework instead. As you can see, this one seems to respond much faster. It doesn't take 1.6 seconds. So why is that? Let's go back to our Jaeger tracing here again. And let's do, again, let's remove this 1 second, and let's say operation vertex instead. Find traces, and here we have a trace. And we can see the total execution time is 232 milliseconds. And you can see the delay here, because we have all the inventory calls is taking 200 milliseconds, but they look to be happening in parallel. Actually, they're not happening in parallel, just that we are doing it in an asynchronously way, in a reactive manner. We're calling the services, and we're not tying up resources. This is just one thread executing, but doing the calls asynchronously. So, and if we go through the performance test now using the reactive one, we're gonna put 12 again here. So it looks fine. No problems with that. Actually, let's jump the speed a bit. Let's do 50. Just to see how the reactive frame works. We can see a bit higher response times because we're executing in one thread and that thread is very busy. But actually, all the responses go through. There's no errors, there's no tying up resources, etc. And this is just an example of choosing the right tool for the right task. I'm not saying that Java EE and Spring is bad. I think we need to select when to use what. And I definitely is one of the advocates for you still using Java EE in a microservices application, because you will still have to connect to backend systems, you'll have your existing legacy code, etc. You don't want to delete all that. But in some use cases, I know like a reactive tool would be more actually preferred to do. So I hope that demo was good for you. So,
all right, so let's
go back to
the
presentation.
We have 9 minutes. So let's go back to the steps and recommendations. Thank you, Thomas, for that wonderful demo. So the fifth step or recommendation on your path to cloud native application development is what we call self-service on-demand infrastructure. And the idea here is that you want your developers to be able to, through a self-service mechanism, to procure their own infrastructure, to be able to quickly spin up an environment to run their tests or run some QA, and but also that necessitates that operations still needs to have control and visibility into the environment. So one good option to be able to do both and to handle both is to use containers, and containers are a good option to provide a whole life cycle of containers to make self-service easy to use by developers. And also, together with containers, you also need an orchestration technology. Kubernetes is an example that also provides this automation and application lifecycle management capabilities to provide this capability. This step that supports this step. So let's move on real quick. Step number 6, or recommendation, is automate IT to accelerate delivery. And in this case, we're not talking just something that is specific to a group, but we're talking about an integrated, full-scale, enterprise-wide automation approach. Okay, so we're talking about creating automation sandboxes for developers to quickly test ideas on. Collaborative dialogue, self-service catalogs, and policies and processes that support this enterprise-wide automation. The 7th step. Yes. Oh, thank you. Thank you. Sorry. Step number 7 is implement CI/CD pipelines as well as advanced deployment techniques. So a pipeline, the goal of a pipeline is to provide updates without operational capacity, while maintaining operational capacity with reduced risk. So this picture right here shows you what a CI/CD deployment pipeline looks like using containers. So the idea here is a developer does a commit in the source repository, which then triggers the pipeline, which then will push out the changes and create the image and the container image, generate a pod, and then deploy that pod and run it. And the nice thing about containers is that they can run on a physical environment. It could run on virtual as well as a public cloud or private cloud. So it gives you containers, and container orchestration technology gives you cloud portability. Other advanced deployment techniques are rolling upgrades. This is the concept of having a router, and basically you have a cluster of running servers, and you take, through the router, you take one server offline at a time, you apply the update, and then you bring it back online, and then you move on to the next server. That's called rolling upgrade. And the idea here is that at the end, you will upgrade everything, and the end user will not notice that there was an update at all. There won't be any downtime. Another deployment technique, advanced deployment technique, is blue-green deployment. Think of blue as your production workload, and the green is the modify workload. And you put it out, the green, into the production environment, and then what you do is you, at a certain point, you move your traffic from blue to green, and if everything goes well, then you take off the blue, right, the blue deployment, and then the green now becomes your production live deployment. Canary releases is similar in the sense that you will deploy your new modified workload into production, but only route a subset of your users to it, okay? And then as you verify that the canary release is working well, then you start increasing the users until your entire traffic is going to the canary release, and then you retire your old release. And A/B testing is similar to canary, but A/B testing is usually used for hypothesis testing. So let's say you have a web app and you want to move a button to another location and see how users react. So you would deploy that as a B test, and then you route a subset of your users to that, and then you collect data, so that statistically you can prove whether it was better or not. So that would take days. Okay, that's called A/B testing. And the last step is evolve a more modular architecture. Microservices are a great fit for cloud-native application development, in that they fulfill the two tenets of cloud-native application development, namely the service-based architecture and API communication. However, if you run microservices on a container platform that includes DEVOPS pipelines, microservices are a perfect fit for cloud-native app developments, because then microservices fulfill all the 4 key tenets of cloud-native application development that we covered earlier. Now, as you know, microservices, they don't prescribe or tell you what architecture or framework or language to use. A microservice is really defined by its characteristics. It has to be autonomous, self-contained. It cannot share any kind of data with another microservice, for example. And it introduces great benefits, not just in the entire development cycle, but also in the maintenance part of it, because you can update microservices independently without having to retest the entire application. So another alternative to microservices, because writing and implementing a microservice architecture is a complex task. It's not easy to do. It's called monolith first. A lot of analysts and subject matter experts have introduced this concept, and what it means is, the ultimate goal is to build microservices, but you start with a monolith. And the reason that you do that is to better understand your domain and the bounded context between your domain through the monolith. And then once you understand and the different bounded contexts, you can start basically strangulating or using the strangulation pattern to start creating microservices out of these identified bounded context. The benefit here is that if you jump directly into microservices, you could run into the issue that you wrote a microservice with the wrong bounded context, or maybe it spans more than one, and then you have to rewrite or break that microservices into 2 microservices because you did not understand your domain well, and that's called technical debt. So in order to avoid that technical debt, the idea here is if you first implement your application in a monolith, and once you understand the domain and bounding context within it, you can then strip out or take out or break up the monolith into the appropriate microservices. Now, not everybody needs to be like Uber. Not everybody needs to be like Netflix. In fact, most organizations are not like them. So a third or a second alternative to microservices is what it's called mini services. And a mini service is a collection of services that are put together or defined together by domain. So think of a mini service as a happy medium between a microservice and a monolith. So a mini service doesn't fulfill every single characteristic of a microservice. You could have a mini service that actually has two services inside that share maybe the same data or the same database table. You can have transactions in a mini service, and and these break the characteristics of a microservice. However, it's an option that will be when it's rolled out, it will be less complex than a microservice architecture. The thing is that also that mini services still require DevOps practices, and they can take advantage of containerization, for example. So you get all those benefits of using a DevOps approach and a cloud native application development, applying one of the 4 key tenets within for a mini service. I'm sorry, and get agility that way. So lastly, we like to cover a couple of customer successes. The first one is KeyBank, which is a large US bank, and they focus on accelerating application delivery and deployment by using containers, container orchestration, DevOps, and CI/CD, as well as automation. And they were able to reduce their deployment time from 12 weeks to 1 week. The second customer success is the Australian Securities Exchange, and they had existing applications that they decided to modernize using cloud native app dev principles, and they were able to migrate and evolve those solutions using microservices and running all under a container platform. The results that they saw were 60 times faster application restart speeds, and also they saw a decreased platform support, cost and time, as well as freeing resources for innovative service development. So lastly, to conclude, I would like to give you this link. Is a bit.ly link, MP-ebook. MicroProfile, as you know, is microservices specification for enterprise Java. And we invite you to go to this link and download the draft version of this ebook. And it makes a great reading, gives you all the background of MicroProfile, as well as how to use the different APIs to implement microservices using this specification. So thank you very much for attending this session, and have a wonderful day. Thanks.
Great.
Awesome. Good. Thank you.